This conference will now be recorded.
Okay, good day everyone. Welcome to the second class of the basic amateur radio course. Today we're going to talk about basic electricity, and this is one thing you don't like if you're an amateur radio operator: lightning. Always scares the crap out of you when lightning strikes close to your antenna. One thing before we get into the lesson, I'm just going to bring up a different PowerPoint here, and let me see here. Yeah, I'll do it at the break. Don't worry about it. It's just some additional study material, but we'll cover it later. Okay, basic electricity. So today, when we're done, you're going to have an introductory knowledge of elementary atomic theory. You're going to understand some of the basic concepts such as conductors, insulators, resistance, direct and alternating current, electromotive force, magnets, cells, batteries, and we're even going to touch on schematics, as in schematic diagrams. So I'm going to be like Sheldon Cooper, and let's go back to the very basics, the structure of matter. So everything is composed of atoms. In fact, you should never ever trust an atom because they make up everything. Oh well, it was a joke. So matter is composed of atoms. Atoms consist of neutrons, protons, and electrons. Now the neutrons and the protons are in what's called the nucleus, the very center of the atom. The electrons orbit around the nucleus. There are over 100 different atoms, different arrangements with numbers of protons, neutrons, and electrons. And those are called elements. Now I say over 100, there are about 98 that occur naturally. There are about another 20 or so that exist only in laboratories. We've managed to make some of them, but they have very short half-lives. So the 98 that actually exist in nature are the ones that we're more familiar with day to day. Anyone know what this is right here?
Hydrogen.
It's hydrogen, but it's a special type of hydrogen. We got any nuclear physicists here today? That's right, Christine. It's deuterium. Hydrogen normally has only one proton and one electron, but in deuterium, it's got a neutron as well. It occurs naturally in nature, but it's a very, very small percentage of water in nature has the extra neutron. And deuterium is what it makes up water in what's called heavy water. And if you know your World War II history, you know that heavy water was used as a moderator for nuclear reactors, and the British sent commando missions in to try to destroy the heavy water plant up in Norway. And the British or the Norwegian resistance fighters managed to sink a ship that had a shipment of heavy water that was on its way to Germany. So exciting stuff. If someone said it's toxic, but you'd have to drink one heck of a lot of heavy water in order to die from it. Anyway, that's it. The protons and neutrons are about 1,800 times bigger than an electron, and this is not really to scale. Most of the area, most of the volume of an atom is actually empty space. And atoms are all arranged in what's called the periodic table of the elements. And they're listed here by their atomic number, which is the number of protons and neutrons in the nucleus, and also by chemical characteristics. And you get up in, someone's got their microphone on. Could you make sure your mic's off, please? Okay, once you get up into these elements up here, these are the ones that we have to synthesize in laboratories, and they don't exist in nature now, but these are the main ones here. And of course, they've all got their symbols, and if you're a Jeopardy fan, you try to memorize all these because they're going to come up in a Jeopardy question sometime. By the way, atoms can gain or lose electrons, and in doing so, they become either positively charged or negatively charged, and those are called isotopes. They can also gain or lose protons, and they can gain a charge that way, and then they'd be known as isotopes. Ions, we're going to talk about quite a lot in chapter 6 when we talk about propagation. Now, electrostatic attraction holds the negative electrons in place around the positive protons. There's also something called electrostatic repulsion that causes like-charged particles to repel each other. So two electrons will try to stay away from each other. Two protons will also try to stay away from each other, but there's something that's called the strong nuclear force, and this only acts in the nucleus of an atom at very, very short distance. But it's what holds the protons and the neutrons together in the nucleus. And the strong nuclear force is able to oppose or overcome the natural repulsion between the protons there. Okay, and atoms, like I said, they can lose electrons, they can become positively charged when they lose an electron, or they can gain electrons and they can become negatively charged. So just another depiction here of a deuterium atom, a proton and a neutron in the nucleus held together by strong nuclear force, and the electrostatic lines of force keep the electron. We visualize it by saying it's in orbit around the nucleus. Nelson, don't worry, this is just background information. There's no nuclear physics in the test. But it's nice to know because it helps explain some of the phenomena that we study in electronics. And remember, unlike attract, like particles repel. Now, molecules are electrically neutral groups of two or more atoms, and they're held together by what are called chemical bonds. And here we've got hydrogen or dihydrogen monoxide. Anyone know what dihydrogen monoxide is?
Water.
Water.
Exactly, dihydrogen monoxide, a fancy name people are given to water, H2O. So it's made up of one atom of oxygen and two atoms of hydrogen. And what they do is they share the electrons in the outer shell. So an electron here from the hydrogen is shared with the oxygen atom, and the same with this one over right here. And that bonds them together and forms water, H2O.
Alan, if there was distilled water, would the molecules still be the same?
Oh yes, yep. In regular water, you would still have this, except you'd have other impurities in the water. The impurities may or may not cause some ionization here, but you know, the water molecule is still a water molecule. Okay, so that's how. And one thing I like to do when people talk about mercury in fillings or in vaccines or something, they don't realize that mercury as a compound with other elements is not the same as mercury by itself. It's not poisonous. And I like to say that, you know, the human body is made up mostly of H2O, water. And yet, you know, so that means you're full of hydrogen, and hydrogen is explosive, and yet we don't explode. And I ask them why that is, and they think about it. And I try to get through to them that, you know, an element in its pure form is not the same as elements mixed together to form molecules. That's right, Claude. Distilled water is not conductive. It's the impurities that add ions that cause water to conduct. Now, there's something that you should know about, and that's valence electrons. The outermost, first I should say that electrons form discrete orbits around the nucleus. There are 2 in the first orbit, their maximum of 2, their maximum of 8 in the third orbit, or second orbit. There's a maximum of 18 in the third orbit, and I think it's 32 in the next orbit, and so on. There's a formula for calculating it. So there's only a certain number of electrons that are allowed in the outer level, the valence electrons, they're called. And these play an important part when it comes to electricity, either forming insulators or conductors or sometimes semiconductors. We're going to talk about semiconductors later on in the course. But here you can see that boron has got 3 valence electrons, silicon has got 4, antimony has got 5. But they've got 51 electrons in total anyway, but they're all in different layers here. And that brings me to conductors versus insulators. You're probably all familiar with it. You know that copper wire conducts electricity and things like glass or plastic don't conduct electricity. But why is that? Why are some materials good conductors and some materials not good conductors?
Depends on the amount of electrons in their valence.
It has to do with valence electrons.
Well, there we go. And that's because conductors, it's relatively easy to dislodge the outer valence electrons, and that allows electric current to flow easily. So most metals, as it turns out, are good conductors. Now, the best conductors are silver, copper, and aluminum. Watch out for aluminum, however. Aluminum oxidizes very easily. Within a few seconds of exposure to oxygen, aluminum forms a layer of aluminum oxide. Aluminum oxide is not a good conductor, but the good news is it's not a very thick layer, and if you scratch it or scrape the aluminum, you'll get down to pure, you get down to the underneath the aluminum oxide, you'll get to the layer of actual aluminum, which is a good conductor. So when you're putting aluminum antennas together, you always got to make sure that you clean them up, and just as you're tightening them, at the very last little bit before the final tightening, I always give my antennas a twist to make sure that they form a good joint. I'll explain more about that when we talk about antennas. Now, gold itself is not actually a good conductor, but the good thing about gold is that it doesn't corrode, and that's why you have gold-plated contacts, because they won't corrode, they won't have poor contact there, electrical contact, when you plug the 2 contacts together, 2 connectors together. So silver, copper, and aluminum. And gold, not a great one, but it's got certain uses. Silver does oxidize, but silver oxide is a good conductor as well. Yeah, aluminum can cold flow under certain conditions, yeah.
Of all 3 that you're showing here, silver, copper, and aluminum, are they in series of which is the best? Because I always noted that copper was the best conductor.
I think it is very slightly, silver is a little bit better than copper. I'd have to confirm that, but the difference is not that great, and the difference in price is great. So copper is much cheaper than silver. Aluminum is probably cheaper still, sometimes, depending on the way the metal market goes. But aluminum does have issues with expansion causing poor contacts.
I think from what I know, why silver is a better conductor is because when silver oxidizes, it just loses color. There's no additional layer over silver. Copper, aluminum have additional layers over them when they oxidize.
Yep, exactly. And like I say, with aluminum, aluminum oxide is a poor conductor. It's actually a good insulator. Cold flow is when you don't actually melt it, but it can still flow under pressure.
Yeah, I cover all my conductors with silver plating for the antennas.
What was that, Yanni?
I build antennas for the U.S. Navy.
Okay.
And all the conductors are silver plate. I silver plate them to have good conductivity of flow of electrons in the outside diameter.
Yep, exactly. Okay. So here's a copper atom. It's got 29 electrons, and but the outermost electron, the valence electron, is by itself, and that means it doesn't have much to tie it to. It sort of feels distant from these inner ones. They form a clique, and this guy says, well, I'm not really part of your clique. I like to travel a bit more. So the valence electron in copper is able to get out and travel around, and that's what happens here. The electrons, if you push them in the right way, the outer electron in copper will go from atom to atom and flow along like this. And electric current is actually the flow of electrons through a conductor. Hope you like this. I stayed up all night making it. And if you believe that, no, I didn't. I found this online.
They're trying to sell a fridge to an Eskimo here.
Yeah, okay. So that's electric current. Now insulators, on the other hand, have valence electrons that are hard to dislodge, and electric current typically can't flow very easily. So typical insulators, glass, rubber, most plastics are insulators. Teflon is an insulator. Ceramics are also insulators. So the electrons in the valence layer, the valence electrons, are very difficult to dislodge, and current can't flow very easily. Now, of course, you can reach the point where if you apply enough voltage, and we're going to talk about voltage in a few slides' time, but you can make any insulator or conductor once because you will apply so much force to the electrons that they will move. But in doing so, you'll destroy the material most likely. Okay, how does grounding affect the flow of electrons? Well, they'll be at ground potential, Abdullah, and we'll talk more about that in chapter 3, and also when we talk about grounding for safety purposes. Now, an electron is pretty small, and in fact, the charge on a single electron, the negative charge, is so tiny that it has no impact on day-to-day life, for most things. So we've come up with something called the coulomb, and the coulomb is the charge, the electrical charge, that 6.24 times 10 to the 18 electrons would have. So that's a whole bunch of electrons. 6.24 times 10 to the 18 electrons. Someone had a question?
Yeah. In the book here, it says 6.28 times 10 to the 18.
Yep. In 2019, there was a change made to some of the definitions, some of the scientific definitions.
Yeah.
And that was one of the changes. And it confused the heck out of me as well, because I mean, my degree is in physics, and I said, wait a minute, that's not the right figure. And then I had to do a bit of research and find out that some of the definitions had actually changed.
Right. Okay, thanks.
Oh, okay. According to the latest, it's 6.24 times 10 to the 18 electrons. And in any event, we're not going to count them individually. But the coulomb itself is used in the definition of the ampere. Now, we do talk about amperes, although for what we're going to be doing, we're not going to be talking about coulombs and that. If you get a degree in physics, then you'll worry about that. But the ampere is the unit of electric current. It's the rate of flow of electrons in a conductor. And it's defined as 1 ampere is equal to the flow of 1 coulomb of electrons, so 6.24 times 10 to the 18 electrons, going past a point in 1 second. So it's the number of electrons past a certain point in 1 second, 6.24 times 10 to the 18 electrons. Now the ampere is abbreviated A, and it's measured in amperes. So, or correction, the ampere is abbreviated A, the current is abbreviated I. So I is current, and I equals 5A, would be 5 amps. So current equals 5 amps. Don't ask me why we just don't say A equals 5A. I guess that would be, it might be too confusing, but current is abbreviated I, and I is measured in amperes. So I equals 5A, current equals 5 amperes. Everyone good with that? Now we measure current using ammeters. Here's a typical one you'll find on a workbench, digital. It's got a whole bunch of different scales here as well, so it can measure current and voltage and resistance. We'll talk more about those later. So that would be a multimeter, but it can measure current. This would be the type that you'd probably see in a high school laboratory, and you can connect the negative terminal here, and then depending on the value, the amount of current you want to measure, you use the different terminals here, and you'll actually read it on the scale, and that's given in amps, or it looks like it could be up to, oh, what is that, 5? Okay, so different scales here for the different scales that are used down there. Now there's also something you'll run across called milliamperes, which are 1,000th of an amp. So if you've got 500 milliamperes, that equals 500 divided by 1,000 amperes, which is half an amp. Now for very small currents, we use what are called microamperes, and there's the symbol, this symbol mu meaning micro here, and those are 1/1,000,000th of an ampere. So it takes 1,000,000 microamperes to make 1 amp, 1 ampere. Why is the current, the designation for current I? I don't know. You'd have to go back to the 1800s, and okay, intensity could be. It was just whatever they came up with. Yeah, and Janice is correct, I think, from the French. And someone said a question on the test. Okay, oops, looks like I missed a few questions here. Okay, I didn't miss that. There we go. And there you go. From Coulomb, the French scientist after whom Coulomb, the unit of charge, is named. Intensité de current, or intensity of the current, which is abbreviated I. There we go. Thank you very much, Janice. Do you have a degree in physics, Janice? Are you there, Janice? She has a Google. Biology and Google. Okay, Janice. Yep. So remember milliamperes and microamperes. You're going to run into them as an amateur radio operator, and you're going to run into them on the test. Michael, we'll talk about that later on, not today. Now, there's one concept you got to you've got to understand here before we go any further, and there's what's called conventional current and electron flow. Now, we know nowadays that electrons flow from the negative terminal to the positive terminal. You have a battery or a power supply, whatever. So it's electron flow that is actually current. But back in the early days of people studying electricity, they just assumed current would go from positive to negative. I mean, it just makes sense, doesn't it? Everything goes from positive to negative. So therefore, current in the conventional system is from positive to negative. And if you take a look at symbols later on when we talk about diodes and transistors, the easy way to visualize is thinking that current goes from positive to negative when it comes to arrows in things like diodes and transistors. But the electron flow is actually negative to positive. Now, it doesn't matter which one you do, which one you use, just as long as you make sure that you use the same convention throughout the circuit that you're working on. So you can either visualize electron flow or you can visualize conventional flow, but just be aware that there's a difference. And yes, there's something called whole flow, but we'll talk more about that when we get to semiconductors, Robert. And yes, there are some cars with positive ground. but that doesn't affect this. This is just the way that the convention that we use to indicate the direction that current flows. Any questions on conventional current versus electron flow? Everyone good? No, it isn't. Don't get into whole flow right now. Okay. And when would you use one versus the other? It just depends on the textbook. If you're using an older textbook, they might use conventional flow. If you're using more modern, they might talk about electron flow, but just know the difference. Is it on the test? I'm not sure. We'll see at the end of this chapter, David. We'll go through the questions. Brad, it's not that current is actually moving in the opposite direction, just that the way we imagine it moving is opposite to the direction of the electrons. It's still electrons flowing from negative to positive. It's just that if you are looking at the direction that current flows, you can also think of it going as positive to negative. And if you do that, then you have to do that throughout the entire circuit when you're analyzing it. That gets into more advanced circuitry that we're not going to be talking about in this course. Yep, and we're not going to talk about holes yet. No, David, electron flow is from negative to positive. Conventional current flow is imagined to be from positive to negative. Just take a look at this up right here. Now, the valence electrons are held in place around the atoms by electrostatic force. And if we want to get those to move, we've actually got to do some work to make them move. And we do that by applying electric charge on the body, by adding electrons. And the way we do that is measured in volts. And this is known as the electromotive force, the EMF, the potential difference, or the voltage. So the voltage is basically the pressure that we put on the electrons to move through a circuit. And we can visualize that by just imagining two containers with a hole down right here. This one doesn't have as much water in it. It's not as high. It could still be very big, but just the level of the water is not very high. So there's less pressure pushing the water through here. In this one, the level of the water is higher, so the pressure on the water down here is going to be much greater. So lower pressure equals lower voltage, higher pressure equals higher voltage. Now, this could be as big as the Pacific Ocean, just that this is the potential difference right here. This is the voltage measured by the depth of the water. So the pressure right here is going to be the same no matter how big this container of water is. It's the height that matters. So voltage is the pressure that pushes electrons through a conductor. Now, I'll throw the scientific definition at you. You don't have to know this for the test, but if you want to know this, 1 volt is equal to 1 joule per coulomb. If you're not into physics, you can forget that. But the symbol is E, and the voltage is measured in volts, V. So E equals 5V, for example. Now, typical voltage on an alkaline cell, a flashlight battery, is 1.5 volts DC, direct current. A car battery, we call them 12-volt batteries, but they're actually about 12.6 volts DC, direct current. The household outlet in your wall is 120 volts AC, alternating current. And we'll talk more about AC and DC a little later on here. Michael, you're getting way too far ahead. Henrys are not involved in this chapter. You're up in several chapters ahead. It's good you're reading ahead, but stick with what's in chapter 2. Now we measure voltage with a voltmeter. Here's another one of these multimeters right here. So it would have several range scales for different voltage levels that you might want to measure. Important safety tip is if you're measuring a voltage, always start with the highest level voltage and then go down. If you start with a low voltage setting, you may damage your instrument. So you think you're going to be measuring 1 volt and it turns out to be 100 volts, you may damage the instrument. So always start on the high scale and go down. This would be the type of volt meter that you'd see in a panel, electrical panel, or maybe in a some type of equipment, and this would measure the voltage directly. If you notice, there's a little mirror in back here, and that's to prevent what's called parallax error. When you take a look at it, if you look at the side of the needle, you look at it from an angle, you might get the wrong reading. But if you look at it and you line the reflection up with the needle in front of it, then you'd see where it is on the scale. You're going to get a more accurate reading. Now, just like amperes, we've got millivolts, which are 1/1000th of a volt, and we've got microvolts, which are millionths of a volt. So 1/1,000,000th of a volt might not be much, but the signal coming into your antenna is probably going to be less than a microvolt. And modern receivers can receive signals down around, easily down around a 1/4 of a microvolt. So very, very weak signal. So that's where you might encounter the use of microvolts.
Al?
Yep.
Yeah. Do you think there's any device which can help us calculate both ampere and volts in one device?
Yeah, they're called multimeters, but you'd have to hook them up to the circuit differently.
Okay.
Yeah. Okay, because you measure voltage and current in different ways in a circuit, different points in a circuit. And diesel, yeah, that is true. Most multimeters are auto ranging now, but if you've got an older one, you've still got to set the right scale.
Okay, thank you.
Yeah. Now, we're going to talk about something here that's futile. We're going to talk about resistance. And there, Roderick, that's a good tip. Make sure when you're using your multimeter, if you're measuring voltage, make sure it's set to voltage. If you're measuring current, make sure it's set to current on the rotary dial. Okay. And if you try to measure current with voltage, you're probably going to damage it. Or at least if it's a good one, it's got a fuse built in, and you blow the fuse. We'll talk about fuse in a little bit here. Okay. And what did I miss here? Okay, yeah, we got that. Okay, didn't miss anything. No, it wasn't Buddha who said that. So resistance is the opposition to the flow of current, and it's measured with the ohm, or the unit of resistance is the ohm. And the symbol is the Greek letter omega. The abbreviation for resistance is R, so R equals 5 omegas, 5 ohms. So we've got current is measured in amps and abbreviated I. We've got voltage measured in volts and abbreviated E. And we've got resistance, which is measured in ohms, which is abbreviated omega here like this. And the abbreviation for resistance is R. So here you can imagine resistance. You don't have a lot of resistance if you've got this current flowing through right here like this. And this current, in this case, is going to be water, but you could visualize it as electricity. And if we squeeze that, we constrict it, we make it harder for the water to flow through. So that would be resistance. And you can do the same thing with electrical circuits, not quite by squeezing a piece of wire, but we've got things that will introduce resistance into a circuit. Does more resistance increase pressure? No, not quite.
More resistance would increase the heat.
It can, yep. Yeah, depending on what it's made of. Yep.
Yeah.
Mark, some oxidized materials are good conductors, others aren't. So resistance could increase if there's oxidization, yes, but not necessarily. So here are some of the factors that affect resistance, the specific resistance of the material. And what that means is that some materials are simply just inherently better conductors than others. Copper is a better conductor than iron. Iron is actually not a great electrical conductor. It does conduct, but copper is much better. So the specific resistance of copper is better conductor than iron. Now, of course, the length of the conductor, longer means greater resistance. And the diameter of the conductor, the greater diameter, the more path there is for electric current to flow. So therefore, the less resistance. So the length and the diameter some people just condense that into the shape of the conductor. The shape determines the resistance. But it's, when you're talking about wire, you're talking specifically about the length and the diameter of the conductor. Now, temperature will also have an impact on resistance. Depending on the material, they can either be have what's called a positive temperature coefficient or a negative temperature coefficient. Now, a positive temperature coefficient means that as temperature increases, the resistance also increases. And that is, most pure metals have what's called a positive temperature coefficient. So when you heat them up, the resistance increases. Now, if you can find an old incandescent light bulb and you take your ohm meter and you measure the resistance of the filament in the light bulb, you'll notice that it's a very low resistance. But when when current starts flowing through it, it gets very hot, so hot that it starts to glow. And when it gets that hot, the resistance is much less than it is when it's cold. Negative temperature coefficient, I'll answer the solid and stranded wire just a moment. Negative temperature coefficient, the resistance actually decreases with temperature. And there are some types of semiconductors, for example, that will do that. And the dangerous thing with these is as they start to get hot from electric current, the resistance goes down, and you're going to learn next chapter that when the resistance decreases, the current will increase, and you get what's called thermal runaway, and the component will burn out because it starts to get hot, and more current flows, and it gets hotter, so more current flows until finally it burns out, destroys itself. So that's positive and negative temperature coefficient.
So
now,
like is thermal runaway like what happens when you short circuit a battery?
No, that's just too much current.
Okay.
But, yeah, but there might be some batteries that have that sort of thing, but it's generally with semiconductors. Now, solid core and stranded wire, you're talking about and when we're talking direct current, alternating current is different, but when we're talking direct current, as long as the cross-sectional area is the same, then they would have the same resistance per length. But as Diesel pointed out, solid core, it's just harder to work with sometimes, and it's more prone to flexing and breaking.
Is there any advantage to solid core over strand? Because strand just seems to be easier to work with. And does strand have more of a surface area than solid core?
Probably cheaper to make, and there might be other reasons for the application, but it just, it depends on the application. There's still, some people or some applications that use solid wire. Janice will talk about semiconductors up in chapter 9. Superconductors, well, we're not going to, there's no amateur radio equipment that uses superconductors, but superconductors are simply cooled so low that they conduct with very little resistance, George. Mike, I'm talking direct current here right now. Skin effect we'll get into when we start talking about alternating current in chapter Chapter 4. Okay. Now, resistors are used in circuits, electrical circuits, electronic circuits. They can be used to reduce the current, and they can also be used to change voltages. They use carbon or high resistance wire. So here you can see the two wires coming out of a resistor, and this shadow on the outside is the overall shape. That's made of ceramic or some type of plastic material. And inside they might have a carbon cylinder. And the length and the cross-sectional area of that carbon, and maybe even the composition, it might have inert clay mixed in with it as well. That's what determines the resistance from this point to this point. There are some resistors that are made of a ceramic tube, and they've got a carbon film that's been etched onto the surface. So the electric current has to go through this spiral here like this of a carbon film, and that gives it a specific resistance from here to here. There are other types that actually have a ceramic tube, and then they take nichrome wire. Nichrome wire has a high resistance, and they just wind it around and connect it one end to the other end here. And that gives a specific resistance depending on the length and the diameter of the nichrome wire.
Alan, what determines the positive and negative of the resistor?
There is no positive or negative of a resistor. They work either way.
So a diode would have a positive negative then?
Yep, that's right. We'll talk about that in chapter 9. The solid wire only goes up to the end caps. The solid wire does not go through. Okay. So the electrical path is going to be up to here, and then through this carbon, and then through the wire. Here it's going to be up to the where this carbon film starts, through that carbon film, and then to the end cap and onto the wire. And here it's through the wire. The end cap is connected to this nichrome wire, through that, a spiral like this, and then to the end cap and on. Nichrome wire would be used in things like your electric toaster. If you take a look in and you see the wire that heats up, that's nichrome wire.
Alan, what kind of thing is used in a microwave? I've seen a big, thick coil in a microwave. I don't know what material that is.
Yeah, totally different. We can bring that up when we talk about a radio, actual radio frequency energy.
Hey guys, just gotta leave. I got a fire call to go to.
Okay, good luck, Ryan. Now here's what some resistors look like. These are the types that you'll see in electrical circuits, most electrical circuits. The bigger they are, the more heat they can dissipate, so the more power they can handle. We'll talk more about that next class. The resistance can still be the same. This is a type right here. This is a ceramic case, and inside is that nichrome wire, and that's wound around, and it's surrounded by this ceramic, and this allows it to dissipate more heat. In this case, it actually dissipates 5 watts. We'll talk, like I say, we'll talk more about that next class. This is a big one right here. This can dissipate a whole lot of heat, and this would be some type of nichrome wire, but it's a nichrome metal, I should say, but it's more like a flat ribbon that's been corrugated like this to make it a little bit longer, and it's wound around this ceramic tube like this. This also gives it lots of surface area, and because it's got lots of surface area, it can dissipate a lot of heat. It can heat up, and then that heat can escape easily into the air, into the environment. So this one would be able to dissipate a whole lot of heat. Now the resistance is not necessarily any greater or any less than this little thing right here, but this can dissipate a lot of heat, and this one can't. So that one would burn up quite easily. This one would not burn up. But we'll talk more about that next chapter. Now, you probably noticed a lot of resistors that got these markings on the outside, and they mean something. It's called the color code, and it's how we determine the value of the resistance of the resistor itself. And by the way, this just goes to show you again how they're made. This one is a carbon composition resistor. So it's got material inside right here. This is where the wire comes in and just is anchored into it. And this carbon composition material is made up mostly of carbon, but there's other agents in there to give it the desired degree of resistance. So it could be some clay in there. And that's all encapsulated in this resistor. And from here to the terminal on the other side, that's the that would give the resistance as it travels through this carbon composition material.
So the flow of electricity can flow on either end of the resistor.
Yep. Electrons are going to enter here and go through and exit here, or they could enter here, go through and exit here.
Okay.
Yeah, resistors are, it doesn't matter what way you put them in the circuit. Now, there's actually a way to figure out what the resistance is based on these colors. And here's a little color code. So the first band in this case is green. We go through and green is 5. So we know it starts with 5. The blue, we go through and blue is 6. So it's 5, 6. Now the third band, when you've got 4 bands like this, the third band is going to be the multiplier. So we've got 5, 6, but we don't know if that's supposed to be 56, 560, 5,600, or even more. So we go through, and the multiplier here is yellow, so it's 10 k ohm. K means kilo, which means 1,000. So we have multiply the 5, 6 by 10,000 ohms. So that gives us 56 times 10,000 is going to be 560,000 ohms. We got k ohm. Okay, so that K means kilo. We'll talk more about that in a later chapter. You know, because the 3 of them are together, and then the one down here is by itself. Okay, the one down here is called the tolerance. Now, the more precisely a resistor is made, the more precise the tolerance will be. If they're just cheaply made resistors, it might be 560 ohms plus or minus 20%. But if it's a precision made resistor, it's going to be 560,000 ohms plus or minus 1%. In this case, it's tan, and we go down and where do we find that? Yep, that color right here, it's our tan gold, plus or minus 5%. So this is a 560,000 ohm resistor, plus or minus 5%. Yep, calibration resistors can be very expensive. There's actually a place in Smiths Falls, Ontario. Yeah, just a sec, Claude. There's a place in Smiths Falls, Ontario, a little place, but they make precision resistors that are shipped all over the world for use in scientific and industrial equipment, where they had to be very, very precise. And Smiths Falls, if you know Smiths Falls, you would never say that there's a high-tech industry there that is producing world-class equipment.
What does the letter F, G, D, C, and that is in the tolerance scale stand for?
Yeah, that must be some note in the diagram I got this from, the book I got this from.
Oh, okay.
Yeah. Okay.
It's not relevant. It's not relevant to the resistor.
Nope, not here right now. No. Okay, in the 5 band, it's the same thing, but if you take a look, these 4 are closer together, and this one is still stuck out a little bit at the end. So you just got to notice the difference in positioning here versus here. So the 5 band code is the same thing. You just go through it, just that it gives a little bit more precision in the amount, in the sense that in defining it. So here it's going to be red, which is going to be 2. The orange here is going to be 3. And what's that? Purple, is it? purple is going to be, or okay, violet. There we go. I don't do colors. So violet is 7. So we got 2, 3, 7. And the black means it's the multiplier is just 1. So that's 237 ohms. And we go through and check the color code, and it's 1%, plus or minus 1%. So 237 ohms, excuse me, plus or minus 1%. But you got to
So
notice
that would
difference
be
right there.
that would be one of the better resistors to buy then.
Well, it depends on your application. If you need a precision resistor, then you'd want to get something with plus or minus 1%. It depends on the circuit. The you know, some circuits it's more important to be close, you know, to have a very high tolerance resistor. Others it doesn't matter. The higher the tolerance, the more expensive it's going to be. Yep, Smiths Falls used to be known for Hershey's chocolate. Now it's known for cannabis. There we go. Now, Abdullah, I don't blame you. You can buy them in packs where the resistance is already, you know, indicated on the pack. And you can always take your ohm meter and just clip end to end and just confirm the resistance. Now, there is a way to remember what the colors are and their value. And this is one of the more polite ones. It goes brown, you know, black, brown, etc. Bad booze rots our young guts, but vodka goes well. But you can, if you do a Google search or you talk to an old electrician, you can probably find all sorts of raunchier mnemonics to help remember the resistor color code. And color code on the test. Let's see, we'll get to the questions here at the end of this. There might be one or two. Now, I indicated earlier that the bigger the resistor, the more heat it could dissipate. And this is some sizes you'd see in you know, your everyday electronic items. So 1/4 of a watt, 1/2 a watt, 1 watt, 2 watt. Now we'll talk more about watts next chapter, but just bear in mind that the bigger the device, bigger the resistor in this case, the more heat it can give off, the more heat it can dissipate and still operate. So if you try to put too much current through this resistor, it's going to generate a lot of heat and it'll burn up. But this resistor can tolerate more heat because it's got more surface area, more physical mass, and can give off that heat and not burn up. Okay. And we'll talk more about this next chapter. Now, there's something called potentiometer. A potentiometer, a lot of you probably call it a volume control, and that's one of the things it does in a circuit. But it's basically a resistor, fixed resistor from end to end here, but it's got a variable connection that can go from here to here. And the way that looks in one of these, the little potentiometer, is you've got a resistance element here like this, and that's connected A and B. So A and B would correspond to here and here. This, by the way, this symbol is a symbol for a resistor. I should mention that. Symbol for a resistor like that. So from here, going through here like this, from A to B, there's a fixed resistance determined by this material in here. But this center connection is attached to this shaft, and you can move that from here all the way around to here. So the resistance between A and W and the resistance between W and B will change as you turn this knob and move the position of this slider on that carbon or whatever the resistive element is right here. So if you've got this slider right down here, there's very little resistance between A and W, but there's going to be a higher resistance between W and B. If I move this all the way over to here, then there's going to be a lot of resistance between A and W and very little resistance between W and B, because it'll just be going right here like this. Okay? And this is an important component in a lot of circuits. It's called a potentiometer.
And the potentiometer right now, which one would be positive and which one would be negative?
Doesn't matter. These are not polarity sensitive.
Okay.
Okay. So a volume potentiometer would use W and B. It would actually use all three. If you just want to use two of these, then it's called a rheostat, and those don't come up in electronic circuits that we're going to be dealing with. It's called a potentiometer because you're actually changing the voltage across here, but don't worry about that right now. We'll talk more about that next class. Yeah, W would be for wiper. Okay. Now, early ones were wire wound. They'd have a ceramic material, and you'd wrap wire around. This wire would be something like nichrome wire, and be high resistance. And this right here, this wiper, would move around as you turn the knob, like this one right here. You could also put it on this type of tube. This one can handle 15 amps. So the fixed resistance is between here, and this is connected to this, which moves back and forth, and that's the wiper for this type of potentiometer. Yep, similar to a variac. A variac is what's called a rheostat. It only uses two of these terminals. Okay. Now, the one you're more familiar with would be probably more like this, where instead of wire, they use this resistive element, and that would be the carbon compound. So some type of carbon mixed with maybe clay or something to give the desired resistance from here to here. And this just moves along. It wipes along here like this. And you can put that in the form like this, where a knob does it, or you can even have a slider where it's the resistive material is underneath here, and you move this back and forth, and that's the slider, the wiper. Okay.
What exactly is the purpose of the wiper, Al?
Yeah, it changes the resistance between here and here, or here and here, depending on the position, and that can be used to control things in a circuit.
Oh, okay.
Yep.
Al, would the potometer be used to control the volume in the ham radio?
Yep, potentiometer. Yep.
Potentiometer. Okay.
Yep. And as Trevor says, it's a voltage divider. We'll talk more about that next class. Now there's this type right here called trimmers. They're potentiometers, but they're designed to be put in a circuit right on the circuit board. You adjust them when you're calibrating the piece of equipment by turning the screw right here, 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 and this type right here, which is like this. And you calibrate it, and then you forget about it. It's inside the piece of equipment, and these are called trimmers, but they're actually potentiometers. That's just that you set them once and you don't have to worry about them afterwards.
How would you know how to trim it or calibrate it?
That would be the technician who's calibrating the piece of equipment. It's not something that you should do unless you know what you're doing.
Uh-huh.
Trust me, when a technician, if your radio breaks, and you go to a technician and you say, yeah, I played with all these things inside of these and other things, he or she is probably going to curse because you've just made their job a whole lot tougher. Because in addition to fixing what's wrong with the radio in the first place, you've now miscalibrated everything. So don't do that.
Just another question, what does the calibration, is it of the current or the voltage?
Oh, it depends on the circuit. It's just the
Okay.
way that the designer set it up. Yeah. Dean, because it needs to act as a voltage divider. We'll talk more about that next class.
So trimmers are not like variable resistors. It is both current and voltage.
No, they're just like this, except that you set them once and forget about them. This,
Yeah.
you adjust your volume all the time, for example. This one does the same thing, but you set it once inside a circuit and you don't have to worry about it anymore. Yeah, set and forget. Okay. Let me see. We'll talk one more thing here about resistance, and then we'll take a break. Now, sometimes it's better or it's easier to talk about how well a material conducts rather than what its resistance is. So we've got this property called conductance, and it's the reciprocal of resistance. Okay, so the unit of conductance is G. G is equal to 1 over R. So that's the resistance. Okay, so G is equal to 1 over the resistance. Now, the unit of measure for conductance is the Siemens. It's abbreviated S. It used to be, if you see in the old textbooks, you see it called the mho, the MHO, which is ohm spelled backwards. But then, more recently, the name has been changed. So conductance G is equal to 1 over resistance, and the unit of measure is the Siemens. So if the resistance is 10 ohms, then the conductance is 1 over 10 ohms, which is going to equal 0.1 Siemens. Okay, any questions on conductance? Question about software program, the way the hardware responds using trimmers. Nope, trimmers wouldn't be controlled by software. Trimmers would only be set by a technician who's actually got the circuit board exposed and is working on it. So conductance. There we go. Well, next we'll talk about magnets, but let's take a 5-minute break. So what time have we got here? To my clock. 3 minutes after, so let's make it 10 after the hour. And I'll stop recording. See you in about 7 minutes.
This conference will now be recorded.
Okay, good. Let's just make sure everything is good here. So let's get back to our lesson. Magnets. Magnetism is one of the 4 basic forces of nature. Without giving class answer, who can tell me what they are on chat? The 4 basic forces of nature. Anyone know them?
Strong nuclear force, weak nuclear force, gravity, and electromagnetism.
Yeah, that's good, but I said on chat.
Oh, I'm sorry.
Okay. Earth, wind, fire, water. No, that's not quite, not modern. And Ken says his wife. Okay. Yep. Okay. Magnetism is one of the 4 basic forces in nature. Gravity is another one. The weak nuclear force is another that is responsible for things like nuclear decay. And the strong nuclear force, what holds the nucleus together. So those are the 4 basic forces in nature. So electromagnetism, I say magnetism, but it's actually electromagnetism is one of those. So it's a force of attraction or repulsion that acts as a distance, and magnets have got north and south poles. And not surprisingly, the north and south pole of the Earth are what we use a magnetic compass to point to. So we can visualize the magnetic field around a magnet by looking at these magnetic lines of flux, magnetic field lines. Where these lines are closer together, the magnetic field is more intense. They always start at the north and they go to the south, so they form loops. Just that these loops that these right here just haven't been drawn all the way around, but it's a closed loop that forms the magnetic field. And like I say, the direction is from north to south. Excuse me. Now, magnetic poles. Unlike poles attract, so you take two magnets like this, you put the north and the south poles together, they'll attract each other. If you take two like poles, so either two north poles or two south poles, excuse me, and you try to put them together, there's a repulsive force and you can't bring them together. We've got, this is your basic bar magnet. The north is generally marked in red, and you can see it stamped in here, N and S for south. You've got a horseshoe magnet, not surprisingly, called that because of the shape. This little bar right here is a piece of soft metal, and that's what's called a keeper. And that just makes it easier for the magnetic lines of flux to complete their path from side to side here on the horseshoe magnet. It's not a magnet itself, although it's magnetized while it's attached to this magnet. And you've got a simple electromagnet where you take a piece of soft iron, like a nail, and you wrap some insulated wire around it, and you pass a current through using a battery, and you'll form an electromagnet. And depending on the polarity, one end will be north, the other south, and if you change the polarity of the battery, the other end will now be south and north down here. And yes, the keeper improves the life of extends the life of the magnet. Now we've got what's called direct current. So the current flows in one direction only. So the electrons enter one end of the conductor and they exit the other end. So that's direct current. And if you take a look here, I've got a scale where time is on the horizontal axis. And on the vertical axis, we've got two things here. We're measuring the voltage and we're measuring the current. And for a direct current circuit where there's only resistance, I turn the switch on. The voltage, if I measure the voltage in the circuit, it goes from 0 to 5 volts in a very short time. It's a finite amount of time, so that's why I've drawn it like this. And the current will also increase. We'll talk more about that next class. And then it's steady until I turn the switch off. When I turn the switch off, the voltage disappears and the current ends. But the current flows in one direction only and it's steady. And the voltage is steady. Okay, and that's direct current. Now, where can we get direct current? Well, one source is friction. When you rub something on a wool carpet, rub your feet on a wool carpet, and you get a static electricity shock, that is actually a source of direct current. So that friction is that causes static electricity is direct current. You can get it from heat. So you take a filament in an electron tube. We'll talk more about electron tubes in a later chapter. But when you heat it up, they emit electrons, and that electron forms a direct current. You can get it from pressure. Piezoelectric microphones, just made up of a crystal that when you apply pressure to it, it actually generates a direct current. You can get it from magnetism. We take a conductor and we move it one way through a magnetic field. As long as it's moving only one way, then it's direct current. If we change the direction that it's moving, then we're going to change the polarity and then we generate AC. We'll talk more about that later. We've got photoelectric sources of direct current. A solar cell. A solar cell, when you expose it to sunlight, will generate electricity that's direct current. And of course, the most common one you're probably familiar with, chemical action, and that would come from a flashlight cell, what you would call a battery, although technically it's a cell. So these are all sources of direct current. Now I mentioned cells and battery. Cell is short for electrochemical cell, and it's any device that converts chemical energy into electrical energy. So your what you call a cell, or what a lot of people call a battery, is actually a cell. A battery is a group of cells. So we put a group of cells together and we form what's called a battery. So a car battery actually is a battery, but a flashlight battery is actually a cell. Now in practice, both terms are used interchangeably. So if you're going to say, you know, get a flashlight battery, I'm not going to give you a hard time because we all use that term. It's actually a flashlight cell, but everyone says battery. Now here's an electrochemical cell. The cathode is actually the negative terminal and the anode is the positive terminal. Don't be fooled by this. The cathode loses electrons that flow here. So the cathode is the negative terminal of the battery. So electrons flow out of the cathode and that leaves it as positive charge on the cathode right here, even though it's the negative terminal of the battery. So always remember the cathode is the negative terminal. And when you get into chemistry, you're going to see symbols like this, but the cathode is always the negative terminal. The anode is the positive terminal. The electrolyte is the chemical solution that the anode and the cathode are placed in that cause metal ions to be transferred from one terminal to the other. And that's what causes the voltage that produces electrons to go from the cathode to the anode. Okay. So an electrochemical cell has got a cathode, the negative terminal, an anode, which is the positive terminal, and an electrolyte, which is the solution that causes the chemical reaction that generates electricity. Now, a zinc carbon cell is a simple one, cheap, and we'll look at this in more detail later. But basically, this is like what we call a flashlight battery. The top terminal, the positive terminal, is actually a piece of carbon. It's a carbon electrode. The case itself is made of zinc. So the zinc forms the negative terminal, which is the cathode, and the carbon forms the positive terminal, the anode. And inside the battery is a mixture of manganese dioxide. And that forms the chemical reaction that generates about 1.5 volts. Now, the zinc carbon cells, they're cheap, but they often leaked if you remember the old batteries. But that's what they look like here. You can get them in all the various sizes.
Can a zinc carbon cell be charged?
No, it can't. We'll talk more about that in a bit. Now, a 12-volt car battery is actually 6 cells. 1, 2, 3, 4, and there'll be 2 more down here, okay? And they're arranged in series. Each one of them generates about 2.1 volts, but as we're going to see in a moment here, you put them in series and they'll generate or they'll produce a total of 12.6 volts. Now, each one of these cells is made up of a plate of lead and lead oxide. And in there is sulfuric acid, and the plates are immersed in that, and that's the electrolyte. And basically, there's a chemical reaction that causes the lead oxide to change into lead and the lead to change into lead oxide. And you can recharge these by reversing the flow of current through, which reverses what happens to the plates. The lead oxide changes back to lead, and lead changes back to lead oxide when the current flows through the opposite direction. Okay, and that's what the inside of a car battery looks like.
I was just curious about sulfuric acid, why they would use that as an electrolyte with the reaction with the lead, or?
Yep, it's what generates the chemical reaction that's necessary to produce electricity.
What exactly, can you clarify that chemical reaction though?
We'd have to get into the chemistry of it, and I'm a physicist, not a chemist, and it would go into far more detail than what we need to cover here.
Okay,
but those diagrams with the S's and the C's and the H's and the numbers and all sorts of things, and the arrows saying this turns into this, that turns into that, and that would be it. But that's far beyond what you need to know for this. just know that depending on the chemistry of the cell, you know, depending on the material that's used for the cathode and the anode, you need different solutions as electrolytes to get that chemical reaction to take place. Okay. There you go. You can read more about how a lead acid battery works there, which should have the chemical, the way the actual lead oxide changes to lead and vice versa, based on the sulfuric acid. Now, I alluded to it here. These are 6 cells that, when put together, form a battery. Each one of those is 2.1 volts, but you put 6 of them together and you get 12.6 volts. But it depends on how they're arranged. If you put cells in a parallel arrangement, you connect all the positive terminals together and you connect all the negative terminals together, then you're still going to get the same voltage. In this case, 1.5 volts, because they're 1.5 volt batteries. The difference here is that you'll get current that will last a lot longer. You'll get 4 times the capacity, the longevity, if you're using 1.5 volts and you're drawing a certain current.
So basically, you're increasing the amperage?
We're increasing the amperage, yep. Now, if we put them in a series arrangement where we've got 1 negative terminal here coming to the outside, but the positive terminal of that battery then goes to the negative of the next one. The positive goes to the negative, positive to the negative, and then we measure the voltage between this positive and this negative terminal right here. We're going to get 4 times 1.5 volts, which is 6 volts. So here we've increased the current that it can deliver. Here we've increased the voltage that it can deliver. Okay. So charging all batteries, you reverse the poles. Well, you apply a current to the battery in the opposite direction that it's supposed to generate it. Okay. So this is parallel and series. And we'll talk about parallel and series when we talk about resistors and capacitors and inductors as well, but you can apply them to batteries. So here, we haven't changed the voltage that this battery pack that can deliver, but we've got 4 times the capacity. Okay, so if we hook it to a flashlight bulb, it'll burn 4 times longer than if it were connected to just a single battery or a single cell. Here, we get a higher voltage, but the current will only last as long as it would for one, but we're able to provide more energy because we've got a higher voltage. We'll talk more about that next chapter. This is what a schematic of it would look like. We've got our lamp, that's just a symbol for a lamp. We've got our 4 batteries right here, and they're in parallel, so positive to positive to positive to positive to one side of the lamp, and the negative terminal to the negative terminal to the negative terminal to the negative terminal to the lamp. And this is what it would look like here. This is a symbol for a cell. Okay, and the flat, the longer of these 2 lines is actually positive. The smaller one is negative. And here you notice that positive is connected to positive, connected to positive, connected to positive, and negative to negative to negative to negative. And we can still measure 1.5 volts here into this load, which is just a generic load. In this case, happens to be a lamp. So Luke, in series, a flashlight that would burn brighter but not longer. That's right. Yep. And Renee, that's right. Your 2 AAA cell flashlight is 3 volts because the batteries are end to end. That's right. Yep. Okay. And cells in series. We got our lamp, excuse me, positive terminal of this battery is connected to the lamp, but the negative goes to the positive of the next battery. The negative goes to the positive, the negative goes to the positive, and then the negative goes up to the lamp. So this is how you can show 4 batteries that are connected in series. You don't have to draw a line in between them. You just draw them together like this. And notice once again, the larger of the two lines in the symbol is positive, and the smaller is negative. So 4 times 1.5 volts gives you 6 volts. Now, someone mentioned rechargeable and not rechargeable. Well, a primary cell or a primary battery cannot be recharged when the chemical energy is consumed. There's a chemical reaction that takes place, and you can't apply electricity to reverse that chemical reaction and recharge the battery. And an example of that would be the zinc carbon cell. You can't recharge it. Now, someone mentioned there are those rechargers out there. No, you're wasting your money. They're not actually recharging the cell. You may think it's recharged because it's taken a little bit of a break, but really what's happened is you'll sometimes get little bubbles formed around around some of the terminals, and it seems the battery is dead, but if you wait a little while, the bubbles will be reabsorbed into the solution, and you'll think that the battery's come back to life. It really hasn't. You've still consumed most of the chemical energy in there, but those rechargers make you think that the thing has come back to life when really it hasn't. Make sure I'm not missing any questions here. Oh, okay. Oh, 1/8 of an amp in the last diagram. Okay. Yeah, don't worry about that. We'll worry about that next class. Okay. Now, there's a secondary cell or a secondary battery. They can be recharged. An example of that would be a car battery, a lead acid battery. And it's sometimes called the storage cell or a storage battery. And in that case, once you've used up some of that chemical energy, converted it to electricity, you can reverse the current flow through the battery or through the cell, and you will regenerate the system so that you can recharge the battery. And like I say, the lead acid battery is an example, but we'll look at others a little later on in this lesson. Now, some of the characteristics of cells and batteries. Let's take a look here. Shelf life. Shelf life is how long the battery will last, while it's just sitting on the shelf waiting to be used. Some batteries will last longer than others. Others will actually self-discharge, and there's little chemical reactions going on inside the electrolyte, and you can't stop those, and they will gradually shorten the life of a battery over time. That's why you try to follow the manufacturer's recommendations for how often you should, if it's a rechargeable battery, how often you charge it, what temperature you store it at, things like that. Okay, but eventually all batteries will die if you leave them on the shelf too long. And you take a look, they've got a best before date marked on the package. The internal resistance is another characteristic of cells and batteries. You got to remember that the material that's inside the battery, the electrolyte, has got a certain amount of resistance. And some batteries, the resistance is relatively high. So when you try to get a lot of current out of a battery, well, the resistance slows that current down and your voltage appears to drop. Other batteries, other cells have very, very low internal resistance, and you try to draw a lot of current and they can provide it. And an example of those types of batteries would be a 12-volt car battery or a NiCad cell or metal nickel hydride. We'll talk about those in a few minutes. But they have very low internal resistances. And if you short them out, they can easily get so hot from the current flowing through that they can cause a fire. Voltage drop we'll talk about next class. Energy capacity. Basically, the bigger the battery, the more capacity it's got. It's a chemical reaction that takes place, and the more capacity in the battery, the more chemical that's stored in there, and the bigger the anode and cathode, the more capacity it's got. And it also depends on the actual chemistry itself. A lead zinc battery doesn't have as much capacity as a NiCad battery, for example, even though they might be the same size. So it depends on the amount, and it also depends on the chemistry of the battery itself. And of course, there's the cell voltage. Different types of batteries, different types of cells have different voltages, and that depends on what they're made of, the chemistry that causes the chemical reaction that creates the electricity. And we'll take a look at a few different cell voltages here now in just a moment. Michael, voltage drop is coming up in a future chapter. And AGM, you're talking about absorbed glass mat. We'll talk about that in just a few moments. Okay, so some types of popular cells, the zinc carbon. Primary cell, which means it can't be recharged. They're cheap, they're readily available. They're only good for low current applications because they've got a high internal resistance. When you try to draw a lot of current from these, then your current output or your voltage is going to drop. We'll talk more about that in a future class, but that's why you can't get a lot of current out of these things. So they're fine for for a small transistor radio back in the day, but you wouldn't want them for other applications. Corrosion can be a problem with these. If you remember your old flashlights, if you put your flashlight away for after camping season, next year you pulled it out, they probably had leaked and ruined the inside of the flashlight itself. And when they're fresh, they deliver 1.5 volts. So that's a zinc carbon. Now, zinc carbons, for the most part, have been replaced by the alkaline. The alkaline is also a primary cell. You can't recharge it. It's similar to the zinc carbon, but it's got a different chemistry and it gives greater capacity. They're more expensive. They've got a longer shelf life than the zinc carbon. They generally don't tend to leak as much, but I still wouldn't leave the batteries in there in a flashlight over over the winter unless you needed it and were using it regularly. Don't freeze them. It's not good for the chemistry. Some people say put your batteries in the freezer to extend their life. Don't do that. And they deliver 1.5 volts. Now you're going to say, well, wait a minute, that's a 9-volt battery I'm showing you, right? What do you think is inside that 9-volt battery? Anyone ever open one of these up?
Multiple cells.
I mean, it's not going to be 2 1.5 volt cells. At 2 1.5 would just be 3, but this is 9 volts. And it's 6 little cells inside here, 3 down this side, 3 down this side, connected in parallel. And that's what generates the 9 volts. No, it's got to be 6, George. 6 times 1.5 is 9. Okay, so if you ever get a chance, you can open one of these up, be careful, and then of course dispose of it properly. So it's like a car battery in a way. Yep, Cynthia? And they're connected in series. That's right, Andrew. Yeah, they look a bit like button cells. Exactly, but they're smaller. So you get 3 of them along here and 3 along here. Oh, did I say parallel? I meant to say series. Yep, they're in series. Okay, there's also a mercury cell. This is a primary cell. It's got a very long working life, years and years. They're more expensive. And the thing about them is they maintain their full working voltage right until the day they die. And because of that, they're used as voltage references in test equipment. They deliver 1.35 volts, but they've got mercury. They're banned in Canada, they're banned in a bunch of countries, and they're very hard to find. I can't ever recall seeing a mercury battery, and you probably won't see them now either, unless you're working on some old test equipment. Delia, it's 6 1.5 volt batteries in series that generate 9 volts. So it is a 9-volt battery. And yeah, Trevor says cameras used to use them. Yeah, but like I say, they're banned in Canada now, banned in a bunch of countries because of the mercury content. Now the NiCad, the nickel cadmium. Believe it or not, NiCads have been around since the late 1800s. They're a secondary cell, which means they can be charged. They're abbreviated NiCad, although NiCad is actually a registered trademark of some company that makes them, but everyone calls them NiCads now. And until recently, they were very popular in amateur equipment. They have very low internal resistance, so you can use them in applications where you've got to draw a lot of current from them. People talk about the memory effect, and the memory effect is possible with NiCad cells, NiCad batteries. And that's where if you repeatedly use a battery on a very regular schedule, where you discharge it, to let's say 70% and recharge it, discharge it 70%, recharge it. After a while, it because of the way that the chemistry works inside and the formation of little microfilaments and that, you can get what's called the memory effect, where if you try to discharge it past that 70%, you can't go any lower. This was something that was always exaggerated in amateur circles. The memory effect was really only noticed in satellites that had very regular charge periods when the satellite was in sunlight and discharge periods when the satellite was in the darkness, in the shadow of the Earth. And that's where it was noticed first. It is possible to get it for, if you're a ham, but generally most of us don't follow that strict a pattern when we're using our equipment that's powered by NiCad batteries. They deliver about 1.25 volts. So that's a NiCad. Like I say,
putting those in a freezer help? Because some cameramen had the battery packs and they were in television. They were all, I don't know if it was supposed to be doing that, but they were putting them in freezers to extend the life.
Off the top, I can't recall, but I would say no. Generally, freezing them is not a good idea. Keeping them cool and dry is a good idea, but not necessarily freezing them. Okay. Fridge might be good, but yeah, not the freezer. Devin asked if you could eliminate the memory effect. Yeah, there are ways, but you got to discharge them and recharge them certain ways, and sometimes you got to put a zap of electricity through to eliminate the little whiskers that form in there. It's best to try and avoid it if you can. Okay. Yep. Your IC2 GAT. Okay. Yeah. Yeah. You can replace them now with nickel metal hydride. And I'll talk about those in just a second here. Let's get down to the bottom of the questions. Yes, they are rechargeable. They're a secondary cell. Okay. And Diesel says they put them in freezers to cool them down after quickly discharging them for flash capacitors. That could be. Okay, there we go. Claude, batteries generally don't create noise for a radio system. They're very quiet electrically. And as Diesel said, yes, they operate best at room temperature. For storage, you might want to keep them cool, but they're best at warmed up. You certainly don't want to use them when it's cold outside. Most batteries will lose capacity when it's cold because it's a chemical reaction. And in general, if you cool off a chemical reaction, it doesn't react as well. Now, the lead acid is also a secondary cell, which means it can be recharged. The most common example is a car battery. They can deliver very high power, high current for brief periods. They're inexpensive, but they got to be cared for. When they're charging, watch out because they produce hydrogen gas. So never charge them in an enclosed area. Always, like I try to charge my battery either outside or in the garage with the garage door open and the battery close to the door. So there's lots of air circulation. So be careful for that. The sulfuric acid, of course, is very corrosive. You don't want to spill it on you. And they deliver 2.1 volts per cell, but 6 cells in series, and that's what gives you the 12 volts. Now, these are good for delivering high current for short periods and then being recharged, like when you're starting a vehicle. There's a slightly different type of lead acid battery that have glass mat in there, fiberglass mat, and they're called gel cells or AGM, something glass mat batteries. Anyway, they're designed more for lower currents for longer periods, like we'd use in an RV or in a boat. Marine battery, absorbent, that's it, absorbent glass mat. Okay, and so it's the same principle, but they're designed a little bit differently so that you can get lower currents for longer period. And Isaac, that's a bit of a an old wives' tale about keeping a battery on a concrete floor. What it might be is that usually if you leave it on the concrete floor in your garage, the floor is going to get cold, and therefore the battery loses capacity because it's cold, but it doesn't actually discharge into the floor. Okay. Now there's a nickel metal hydride. It's a secondary cell, which means you can charge it. The abbreviation is NIMH, nickel metal hydride. It's related to the NiCad, but it's basically supplanted it. Where people used to use NiCads, they now use nickel metal hydride because they've got greater capacity than NiCads. They self-discharge at 4% per day. So if you start off with a battery at 100% charge, well, after one day, it's going to be down to 96. And then it's going to be down 4% of 96. And then it's going to be down 4% or whatever that was. So eventually the battery will discharge to the point where you won't be able to use it for very long. You'll have to charge it up again. Now, this is critical. Use only the chargers for nickel metal hydride batteries or cells. Don't use an NiCad charger on a nickel metal hydride and vice versa. They deliver 1.2 volts, so just a little bit less than a NiCad, but you got to use the right charger.
Is it because of the voltage?
No, because of when the charger knows to turn itself off. The point is different with nickel metal hydride and NiCads. And Roderick, I don't know if they tolerate a float charge. It probably depends on the charger. Okay, Mike says they do. And they get a continuous float charge all day. There you go. So they can tolerate a float charge. Okay. The higher the cold cranking amp simply means that the battery is bigger and can provide more current over a short period. And that would be related to internal resistance, but it's because it's a bigger battery. Wade, a float charge is just a low level current that's applied to it at all times, such as if you left it in a charger, it would just be a low level current that just keeps the charge topped up. Trickle charge, yeah. Okay, interesting bit of history there about the wooden case that the glass cells were in. Okay. Now there's lithium cells. Lithium cells are primary. They're more expensive than alkalines, and they're sometimes called lithium metal. They're usable over a wide temperature range, and they're often used as memory backup in computers, also used in pacemakers and medical devices, and they can last a long time, 15 years or more sometimes. Depending on the exact design, they deliver 1.5 to 3.7 volts, and you will encounter these in circuits where you need a little bit of voltage after the power is, after the radio has been turned off to maintain things like memory. So you'll end up eventually having to replace this type of cell in a lot of radios where you want to maintain the memory for memory channels and settings and things like that after you unplug the radio. Second here now. No, these, oh, no, you're thinking of another type of lithium, Nita. We'll cover those in just a second. The lithium cell like this is a primary cell. Okay, you can't recharge these. Now, one thing about these in a radio, they'll have the terminals, the wires spot welded to them. You can't solder because the solder difficult to solder to the case of the thing. And you'd also overheat the battery and cause it to well, I won't say explode, but certainly split. So if you are going to attach a terminal to these when you're replacing it, you've got to go to a battery place that can do some spot welding and just spot weld the tab on there. And if you want to do a proper job and you figure you're going to have the piece of equipment for a long time, instead of having to spot weld the terminals to the battery, just put in a battery holder and solder that in place. Okay, Roderick, there you go. They shorten the life of the cell, yeah.
Al, I was just wondering about the current and the voltage. If you have more voltage, does that diminish the current and vice versa? Or is it just to do with the capacity? Or?
The voltage depends on the chemistry of the cell itself, the materials that it's made of, and that the electrolyte is made of. So, the voltage is a set parameter, no matter how how big or how small you make the battery. If you have that chemistry, that certain setup, then it's going to be fixed. The voltage is determined by just the chemistry. But in general, the bigger the battery, the bigger the cell, the more capacity, the more current it can provide over a longer period.
So more voltage means more current?
Yeah, but we'll in a circuit, yes, we'll talk about that next class though.
Okay.
But the voltage out of this battery, you can't increase. It's determined by the composition of the battery itself. Okay. I hope you see the difference there, what I'm trying to get at. Now, that's the lithium cell. That's primary, but there's also lithium ion, and that is a secondary cell. You can recharge lithium ion cells. Okay, the abbreviation is LiION for lithium ion, or sometimes LIB. These are great batteries in some ways, very high energy density, no memory effect, low self-discharge. So you can charge them up and put it on the shelf and it won't discharge much at all. And it's got low internal resistance, so they can generate a lot of current. But they're also a safety hazard. They're flammable and explosive if you damage them, if you charge them incorrectly, or if they get shorted. If you, and I've seen some videos of these, if you drive you break one of these open, or you shoot a bullet through it, stuff like that, they'll actually burst into flame and they can explode. If you charge them incorrectly, they can burst into flame and explode. I was looking at using these for a balloon project to help out a high school a few years ago, and I looked at it and I said, holy crap, if we were to keep some of these batteries, they'd have to be kept in a metal container because they're so darn dangerous sometimes. Consumer batteries, they have pressure vents, they've got overcurrent and thermal protection battery management system built in. If you were to actually, look inside one, I don't recommend you do, but you'd see circuitry inside, pressure vents and fuses and things like that to protect them and keep them from catching fire or from starting, from exploding. And needless to say, you've got to use the proper charger with these. If you try to charge them without the proper charger, then you're gonna cause an accident. You're gonna cause them to blow up or whatever. And yeah, they are banned on some flights. And yeah, you got to be careful with these. There were some laptops that caught fire. Some cell phones. I think it was Samsung had a cell phone that caught fire with these things. Yeah, the Samsung Galaxy, that's it, yeah. The voltage, what is the voltage of them? I forget right now. several volts. I forgot to look that up. I forget. Anyway, we can look that up. Oh, wait now. Have I got it here in my notes? Doggone it. I forgot to put the voltage down. I'll have to take note of that. Someone says 3.3. I don't know. Picture says 3.7, does it? Okay. Well, there we go. I'll have to look that up. 2.1 to 2.4 volts. There we go. Okay. So that's lithium ion. Do not fool around with the charger for these. Don't damage them. Don't shoot a bullet through them. Don't break them open. Yeah. Because this is what can happen. That's a picture, one of them self-disintegrating. That's a cell phone that overheated when the battery overheated, and that's what resulted. Here's a computer that had an accident. Imagine that happening in an airplane. Not good. And of course, a lithium-ion battery in a vehicle. That's what can happen. Now, they're a Class B fire. Class B means that it's a flammable liquid. They're not Class D. Class D means it's a flammable metal. You can use a ABC, BC, or a carbon dioxide fire extinguisher on them. The lithium is not pure lithium. It's lithium in, forms a compound inside. So it's actually a Class B, not a Class D fire, for those who know about firefighting. Okay, LiPo, similar to yeah, okay. There are all sorts of variations on the battery technology now because they've made a lot of rapid advances. And yeah, the Tesla has a LiPo. Now here's some capacity. Here's a lithium battery. For an AA battery, it's got 3,000 milliamp hours. So 3,000 milliamp hours, so 3 amp hours. That means that it could deliver 1 amp for 3 hours. An alkaline, depending on the exact type, has between 1,700 and 3,000 milliamp hours. A milliamp hour is a way to determine the capacity of a battery. And it's for a bigger battery, it would be amp hours. The number of amps it can deliver for an hour before the battery would be considered to be dead. Okay, for smaller batteries, we say milliamp hours, so thousandths of an amp hour. So lithium, 3,000 milliamp hours. An alkaline, between 1,700 and 3,000 milliamp hours, depending on the exact capacity or exact type of alkaline that's used. A rechargeable nickel metal hydride, between 1,300 and 2,900, depending on the exact brand and the use. Rechargeable NiCad, you can see a NiCad has much less capacity than the nickel metal hydride, between 500 and 1,100 milliamp hours. The zinc chloride, we didn't discuss it, but zinc chloride, 1,000 to 1,500. And the zinc carbon, you can see down here, has got the least energy capacity, between 400 and 900 milliamp hours for a typical AA battery. So you can see a lithium and alkaline have lots of capacity. Rechargeable nickel metal hydride got lots of capacity. The others, not so much. But the disadvantage of the alkaline is that you can't recharge them, whereas you can recharge the nickel metal hydride that you'd find in things like handy talkies, the radio, the walkie-talkies that hams use. Zinc chloride, that's just got to do with the chemical reaction, Dahlia. I'm not sure exactly how that battery works. Yeah, it's in the electrolyte, exactly, but something just happened to be a diagram I found online. Now, when it's time to get rid of your battery, just toss them in the garbage. Who cares, right? I mean, you know, it doesn't matter that they've got toxic chemicals and materials in there. And oh, I got a few people saying no. Okay, take put them in a container and take them to your local recycling center, and they'll dispose of them properly. Hopefully, they'll go to a recycling center where the metals and chemicals can be recycled, reclaimed, and used in new batteries. Yeah, don't throw them in the fireplace, Wade. Okay. Now, a few more concepts. A closed circuit means that the circuit is complete and current will flow when voltage is applied. An open circuit means that there's no path for the current to flow, and that could be deliberate, such as a switch, or accidental, such as a broken wire. So here's an example of a closed circuit. You got your cell, your battery, and you show that you connect it up to the light bulb, and you form a path and current will flow. Now, just notice that they've got the arrows coming from positive going through the bulb to negative. Is that conventional current or electron flow? Anyone know?
It looks like conventional because it's positive to negative.
Yep, that is conventional current flow. The electron flow actually goes from the negative terminal through the filament and then to the positive terminal. So that's conventional flow. This is an open circuit. You can see that the wires come disconnected from the light bulb. The light bulb doesn't light up, electrons can't flow, and the current path can't be completed. So that's an open circuit. Michael, we'll talk about that when we do the questions. More examples of an open circuit. The switch is open, so current can't flow, or you might have a burned out fuse. We'll talk more about fuses there, but the fuse prevents current from flowing. That's what it's designed to do. And you have resistors. If you put too much current through the resistor, you might burn it up and create an open circuit. You could have a short circuit, and that's an abnormal connection of relatively low resistance between 2 points in a circuit. A short circuit is something you generally try to avoid. So in this case, instead of current going through the light bulb, someone has taken a wire and they've bridged the wire across the light bulb, and that's created a short circuit. So the current, in this case conventional current, will use this path right here because it's low resistance compared to going through the light bulb. Your light bulb won't work, and you could very well overheat the wire, damage the battery, cause a fire even.
At what point does it become a short circuit? Like, when does the load be low enough to be considered a short circuit?
Well, generally a short circuit means that it's low resistance. You know, I mean, if I put a 10 million ohm resistor in here, that really wouldn't be a short circuit because it would be much easier for the current to go through the light bulb. But if I just put a straight wire there, then that would be a short circuit.
No, but how much? There's no like, what would be considered a load? Like, how much resistance do you need to be for it to be classified as a load and not a short circuit?
Well, that's going to depend on the circuit itself. I mean, you know, the application. If you're talking about you know, a huge electric motor, it's going to be a lot of load. But if you're talking about a single light bulb like here, it's going to be a very high resistance, so you're not going to have a lot of current flowing through anyway. Yeah, there's no exact cutoff. Just a short circuit is generally just you know, a low resistance path where it's not supposed to. Okay.
Thanks.
Don't get too hung up in saying, well, that's a short circuit, but this one has got 5 more ohms. That's not a short circuit. Doesn't work that way. Yeah, it's all relative, like Ryan said. Here we've got a fuse, and a fuse, if you have a short circuit you're going to get too much current through the circuit, and the fuse has got a piece of metal in there that will get hot the more current goes through. And eventually, if more current goes through than is supposed to be in that circuit, it gets hot enough that it melts. And by melting, it therefore breaks contact and makes it an open circuit. So this fuse has been used and has done its job protecting the circuit. This is a newer, well, this is a new fuse that hasn't blown. Okay, so that's the purpose of a fuse in a circuit, is to detect when there's too much current going through a circuit. When it is, it will open up, create an open circuit, and prevent current from flowing, thereby preventing the battery from overheating, preventing the wires from overheating, and preventing something from burning up. A breaker is an electromechanical device that operates in a similar, has a similar purpose, but doesn't operate this way. A breaker, you can reset. A fuse, you have to replace. Okay. Now, never replace a fuse with a bigger one than is recommended by the manufacturer. So if you've got a 5 amp fuse that blows, don't replace it with a 10 amp fuse. You're defeating the whole safety aspect of a fuse. And it's not just current restrictions, you've also got to make sure you're replacing it with a fuse that can handle the voltage as well, because if there's a high voltage, yeah, that might look like an open circuit, but if you've got 10,000 volts, it's just going to keep jumping across there. It'll arc across there, no problem. So you got to make sure that you follow the manufacturer's recommendations for the current and the voltage specifications for the fuse. Now, if you keep blowing a fuse, investigate, find out why. There's something wrong, and there's a reason for that fuse to be blowing. Fix the problem before you replace the fuse.
Alan, should the fuse be on the positive side of the circuit or negative side of the circuit?
It doesn't matter in actuality, but it's it's generally going to be on the positive side, I believe. But it doesn't matter. It'll work anywhere. Depends on how the manufacturer puts it in, but it'll work anywhere because it's always the same current going through. Okay, before the load, yeah. But given that, you know, electron flow, it really doesn't matter. Now here's a schematic diagram. We're past fuses now. Any questions on fuse? Here we've got battery, and we've got an ammeter, and we'll talk about more of this next class, but the ammeter is connected in series with the resistor. The resistor is the load, and then it goes back to the battery terminal, and we measure the voltage across the battery terminal here. And if you look at a schematic, this is what it looks like. We've got our battery right here generating, providing 12 volts. Our voltmeter is connected across the battery here to measure the voltage of the battery, which is what it's doing here. Notice that there's a positive terminal on the voltmeter and a negative terminal on the voltmeter, and those go to the appropriate sides of the battery. Don't hook them up backwards or you could damage the voltmeter. The ammeter is always in, so the voltmeter is in parallel across the battery or across a load later on. We'll talk about that. The ammeter is always in series. It measures the current flowing through, so it's got to be in series. Ammeters also have a positive and a negative terminal, so you've got to make sure that the positive is connected to the positive side and the negative goes through and is connected to the negative side right here. So that's what it would look like in real life, and that's what it looks like in a schematic diagram. So we'll be looking at schematic diagrams in in some of the future chapters. So you need to know what these represent in real life. Your wife has got a short fuse, okay. And what was the question you asked there? Why the positive side to what I'm in? For the voltmeter and ammeter? Oh, the fuse. Okay. Okay, I think we just got one last topic here. What time is it? 4:08. There we go. So, alternating current. The current flows in one direction and then another at a regular periodic rate. The number of alterations per second is the frequency. In North America, we have what we call 60 cycles per second, or 60 hertz. So if you were to measure the voltage coming out of your wall socket, it's going to be alternating between positive and negative 60 times a second. And 1 cycle per second is called 1 hertz, named after Heinrich Hertz, the guy who discovered radio waves, and it's abbreviated Hz. So 60 hertz means 60 times per second it changes. Now, direct current flows in one direction only. Alternating current flows in one direction and then the other direction in a regular sequence. So here we've got direct current using a battery. Current flows in one direction only. In an alternating current a circuit, we've got this, which is just a symbol for the source. It could be a generator, it could be the wall socket, whatever. And the current goes back and forth at a regular rate depending on the frequency of the source. If we were to look on an oscilloscope, this is time and this is voltage, positive voltage, negative voltage. The direct current would just be a straight current all the way across, doesn't change. Alternating current forms a sine wave. Positive, then negative, positive, negative, positive, negative. So it alternates. Now there are reasons for using alternating current in our home. We won't go into those right now, but we often have to convert alternating current to direct current depending on the application. And we'll talk more about that in what's it, chapter 9 or chapter 10, I think it is. Yeah. Yeah, there's the reasons for using alternating current very quickly. It's easier to produce a very high voltage alternating current, send it on our transmission lines long distance without much loss, and then convert it down to a lower voltage using transformers. We'll talk about those in chapter 4. Okay. So the symbol for a battery, a DC source, symbol for an AC source, that's supposed to be a sine wave in there. Didn't come out very well. And here. Lauren, you're not coming across very clearly. Once again, we've got our voltage and time. Direct current is just a straight voltage, doesn't alter. Alternating current source, the voltage is positive, goes down to 0, negative, up to 0, and that'll carry on. And in just a straight resistive circuit, the voltage and the current are in phase, so as the voltage increases, the current increases. That's only in a straight direct, in a straight resistive circuit. We're going to see that there are exceptions to that in chapter 4. Kevin, we'll talk more about that later. Now, an elementary generator, I'm going to cover this very quickly. We'll talk about it in more detail in a later chapter. But basically, a generator just is a loop of wire, actually many loops of wire, that's in a magnetic field. And as it rotates through the magnetic field, it generates an alternating current. And as it goes through, you can pick that current up, and you can actually measure the voltage, and you can see what way it's going. And we'll talk more about this next class, or I think it's chapter 4. So you can review it right now and read the explanation that comes with it on the PDF. But just shows you how as it rotates through a magnetic field, the coil in a generator will produce this sine wave like this. Now, one thing about an AC waveform, an alternating current voltage or waveform, we call them, this like this. To have the same energy as a direct current circuit, the AC voltage has got to be higher. The peak has got to be higher. Now, basically, the amount of energy that's sort of in this waveform, in this alternating current, is defined by the amount of space, the area underneath that curve. Here, 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 that. Now, as you can imagine, a direct current at the same voltage going across doesn't lose out on these little bits here that don't contribute to the waveform, the energy. So to compensate for that, in order to have the same equivalent energy as direct current, the peak AC voltage has got to be a little bit higher. And if you do the math, it turns out that the peak AC voltage has got to be equal to 1.414 times the DC voltage, or the DC voltage is going to be 0.707 times the peak AC voltage. And that's what's called the root mean square value, the RMS. Now, if you go through and you do the mathematics, you'd realize that 1.414 is the square root of 2. And anyway, there's a mathematical reason for it, but just know that the 120 volts that's in your AC wall circuit, if you could measure the instantaneous or the peak power, it's actually going to be about 170 volts, not 120. And here's an example. Now, the energy under this curve, these two right here for one complete cycle, in blue, in order for it to equal the energy in this green square, which is a direct current, okay, this peak has got to be higher than the DC current. And therefore, what we call 120 volt root mean square, which is what we measure out of our wall socket, the peak voltage is actually about 170 volts. And that's because, as I say, we lose some of the energy that would otherwise be present in a DC circuit. So for the area for this and this to equal the area here, and these are just one cycle, so it's the same amount of time, that's why this peak voltage has got to be a bit higher than the DC voltage. The voltmeter will only show the RMS. You'd need to get a special meter to see the peak voltages. The RMS is basically the average voltage is what you're seeing there, and that equals the 120 volts. Okay. Everyone understand that? So as I say, our peak voltage is actually about 170 volts. 170 times 0.707 comes out, I rounded it off, it's 120.1 or something volts. But 120 volts.
Al, I'm looking at the curve here. If the curve was tighter,
if the frequency
like
changed,
if you're looking in an oscilloscope, you know, and you're looking, what's that?
You mean if the frequency were different? Still the same mathematical relationship?
No, right now I'm looking at the curve here and going, okay, if the curve was looser or tighter, what differences would it indicate to me?
Yeah, all you're doing is changing the frequency, but the mathematical relationship stays the same. Okay.
Okay, so 120 volts would still be 120 volts.
Yep, even if you changed it to 50 cycles or 120 cycles, whatever. Yeah.
Yeah.
Okay.
Okay.
Mathematical relationship should still be the same. Now, you can't just change, you just can't use equipment that's designed for 50 hertz on 60 hertz system. There are other considerations that come into play. Okay, but the root mean square voltage should remain the same. And one last thing, the difference between a sine wave and a square wave. A sine wave looks like this. Okay, and the square wave is just like it's almost like a DC voltage, and then changes to opposite polarity, then up to positive polarity, like that. So that's the difference between a square wave and a sine wave. A square wave, just because of a certain mathematical considerations, it's going to generate a lot of hash, and you wouldn't want to use that in a circuit close to a radio because it would generate a lot of interference. But it also helps me to illustrate the difference between if this were just a DC voltage along here, you can see this area right here and this area right here. That is energy that the AC form doesn't have. And that's why the AC waveform has got to have a higher voltage in order to make up for what it doesn't have under the curve here and here. Okay.
What do you mean by pure sim wave or simulated?
A sine wave. Is that what you asked?
Yeah, and the AC inverters that you buy for like vehicles.
Oh, okay. Yeah, you're talking about inverters. Yeah, inverters try to generate as close as possible to a sine wave. Some are better than others, and because they have to sometimes digitize it, you will get some square waves that are sort of superimposed on it, and they can cause interference. That's why you got to get an inverter that's got a lot of filtering and is well designed if you want to use it on electrical radio equipment. Yeah, a pure or true sine wave. Yeah, some of them are not a very nice looking sine wave at all. Some of them are better when you're talking about those inverters. Okay, Jerry. Yeah. Yeah, a friend of mine picked up an inverter a while ago, so we took it to Fred VE1FA, and we flashed it up and measured the voltage, looked at the voltage on the oscilloscope, and you could see how the waveform was a little bit different from a sine wave, but it was actually pretty good, and there wasn't much interference. Any questions on what we covered here so far today?
Yeah, Al, it's Carl Fisher. I thought you did a pretty good job of delivering everything. I'm wondering if there's a way to disable this dialog box that shows up in the right-hand corner of the screen. I'm seeing a lot of comments up there that have nothing to do with the course whatsoever, and I just find it a distraction. And
Yeah,
I imagine quite a few other people do as well, and I don't quite know what people don't get about that sort of behavior on this. Thank you.
Yep, that's a good point, Carl. The chat box should only be used for questions to me. I glance at it. I can't keep an eye on it, so there's probably questions that have scrolled by because people are chatting about other things. So please use the chat box only for questions or relevant, pertinent comments to what I'm discussing, and just avoid using it for anything else. Okay. As the class goes on, hopefully that people understand that's how it goes. Okay, let's get into some questions for you. How do you find, and what I want you to do is just indicate in the chat box what your answer is. No class answers, just indicate in the chat box, type it in, hit enter when you you got it here. How do you find a resistor's tolerance rating? I think everyone's got that by reading the resistor's color code. Yep. What color band would differentiate a 120 ohm resistor from a 1200 ohm resistor? Most people are saying A, and it is indeed the third band. Third band, of course, is the multiplier. Why do resistors sometimes get hot when in use? People are getting it now. Because some electrical energy passing through is lost as heat. Anytime something gets hot in a circuit, that's energy that is being lost. It's actually energy that the heat comes about by because it's moving. Whoops. I got a metal roof installed just a few weeks ago, and I just had a big pile of snow come down. Looks interesting. Anyway, I don't know if you heard that as it fell. Electrical energy causes the atoms to vibrate around, and that generates heat. So anytime that you've got a component that's hot, that's because the electrical energy is causing the atoms to vibrate and generating heat. The letter R is a symbol for reactance, resistance, impedance, or reluctance. Yep, resistance. I'd say everyone got that. A cell that can be repeatedly recharged by supplying it with electrical energy is known as a primary, a secondary, a low leakage, or a memory cell. Yep, a storage cell. An alkaline cell has a normal voltage of 1.5 volts. When supplying a great deal of current, the voltage may drop to 1.2 volts. Why is this? It's due to the cell's what? Most people got it. Internal resistance. We're going to see next chapter that voltage gets dropped across a resistor, a load. When the current becomes pretty high, you got to take into account that current is being dropped across the resistance inside the battery. So the voltage you measure is going to be less than the rated voltage of the cell. To increase the current capacity in a cell, several cells should be connected in parallel, series, parallel resonant, or series resonant. Got a bunch of answers here, A's and B's. So we don't want to increase the voltage, we want to increase the current capacity. Okay, parallel. So positive to positive to positive, negative to negative to negative. Doesn't increase the voltage, but it increases the current capacity of the cell. Battery capacity is commonly stated as the value of current delivered over a specified period of time. What is the effect of exceeding that specified current? Now, I didn't go into this explicitly, but if you understand it, it should be, you should understand, or you should come up with the answer. I think most people got it. The battery charge will not last as long. If it can generate, if it can provide 5 amps for 1 hour, and you try to draw 10 amps, it should only last half an hour. Now, the scale, you know, the relationship isn't exactly linear, but that's in general, that's what happens. You try to draw a lot of current, the charge is not going to last as long. Which of the following is a source of EMF, electromotive force? Yeah, I think that's a pretty easy one, a lithium-ion battery. To increase voltage output, several cells are connected in well, if the other one was parallel, this one's got to be series, isn't it? A lithium-ion battery should never be yeah, that's a no-brainer. Should never be short-circuited. Any questions?
Yes, where would I find all these questions for the tests for the electrical part that we just looked at? Would it be under the circuit components or?
I forget the name of the exact section, but if you go through the question bank from Industry Canada for ISED, then you'll come across them. I'll be sending you in a later class. I'll be sending you some other stuff with questions on it that is broken down more into sections. It'll be easier to find there, but it's not the up-to-date question bank as you'd find on the Industry Canada website, though.
Okay, so if I want to review this section, let's say for the questions that we just went through, That would
Mhm.
be in the electrical component of the test or the exam?
I don't recall off the top of my head what the name of the section is about in the question bank.
Okay.
It's probably going to be something like basic electricity or something like that. You'd have to go through and you'll find it.
Okay.
Yeah.
Because I guess each different section has are they all divided equally, let's say in 100 questions, or
Each section has got a bunch of questions, and from each particular section, they take one question for the exam. Okay.
Okay.
Yeah. Now, question here. Advanced qualification over basic. There's reference to being able to repair radio equipment. Yeah, you can do basic repairs if you're a basic licensee, but you can't you can't get in there and work on transmitters and things like that and get it deep into the circuit. Okay, it's basically you're not allowed to build a radio from scratch, a transmitter from scratch. If you're a basic, you've got to have your advanced qualification for that. Okay, scroll down, see what I missed. Yep, the slides are currently available on the Annapolis Valley Amateur Radio Club webpage. So David says it's in section 3. It could be. I don't have the sections of the question bank memorized though. Yeah, and if you go to the success page on the COAX publications page, they've got questions there based on the chapter. EMF is electromotive force. That's another word for voltage, Longfei. Okay.
Hey, Al.
Yep.
Hey, so just 2 questions here. I want to get my Morse code as well in the basic qualification. Is there a resource that I can go online? Because I'm pretty good at tapping, but I can't, like, I got to get my receiving kind of up to snuff. Is there a resource online where I can like listen and translate, or?
There are. I don't know the name of them off the top of my head, but if you Google, you'll find a bunch. There would be a bunch of places that that can do it. There's also a few hams in Canada that have CW courses,
Okay.
and I'll be giving you information about them later on once we get close to you know, to the end of this course, that you can follow their course, and they have practice online, and he can coach you and everything.
Okay, and the last little bit there I had was at the end of the course, because I don't think anybody in Marathon, Ontario is certified to actually like give the exam, so I can do that online.
What was that? You can do what online? I'm sorry?
Take the exam.
Oh, yes. Yep. The exam can be done online.
Okay. Yep.
Yep. And again, to be instructions as who to contact to arrange for that given at the end, you know, near the end of the class.
Okay.
Okay.
Thanks.
And Jerry, yeah, it's that's a common mistake. International Telecommunication Union or Telecommunications Union, and I forget which one it is right now. And I got picked up for that when I was drafting up something, and I forget which one it was right now. So now I've got to look it up to see if it's ITU is International Telecommunication or Communications Union. Paul, if a resistor becomes defective, it can go defective in a bunch of ways. It might burn out so that it's an open circuit. It might become a closed circuit, just you know, no resistance. More likely, though, what happens is as they age, the composition of the material inside the resistor changes, and the resistance changes gradually over time.
Okay, thank you.
Okay, Renee, yeah, just the bottom peak or top peak. There might be terminology for it, but nothing that I know of right now. And yes, Mike, you need to have the advanced to do work on club repeaters. Basic can go up and help, but you got to have an advanced as a sponsor for it anyway. Okay, John, fine on that. Okay, Christine, we'll see you later. Okay. Yep. Remember I'll send a link out for the recording tomorrow. I'm just going through everyone's questions here now, and you'll be able to go through this again. And Mike has got a reference there for one of the Morse code sites he's found online. There's undoubtedly lots. Okay. And Emin has looked it up and he says it's telecommunication. There's no S. I'll try to remember that. Okay, a bunch of other people to say it's singular. There we go. Okay, Devin, what do you got? The average of the peaks. Okay, it's not so much the average of the peaks. It gives the average value of electrical energy. And without going into more detail, that's about all you can say. To get the same energy over a certain period of time, the peak AC voltage has got to be greater than the DC voltage in order to give deliver that same amount of energy. The 1.414 is what you would multiply the DC voltage by to get the what the peak voltage, AC voltage would be, and the 0.707 would be the what you would multiply the peak AC voltage to determine the RMS value. And if you take a look at it, 1 over 1.414 is 0.707, and 0.707 over, or correction, 1 over 0.707 is 1.414, and that's all got to do with the math. 1.414 is the square root of 2, so if you want to get into the detailed math, you'll see how that works out there. Okay. It's something we could go into more detail with, but the simplistic explanation would be just for what you need right now. And that's right, there's no class on Thursday because I have a RAC board meeting. Holy crap, lots of questions coming in. Richard, I don't know anything about the app for tests. Some people use it. I don't bother doing anything like that on my phone, I'm afraid. Okay, I'm almost down to the bottom here, I think. Yes, Gabriel, you can leave GoToMeeting. I'm just answering people's questions here right now if they have questions. Okay. Now, one last thing. Any of the Sea Cadets still here? Any of the Sea Cadets here?
There might be a couple of us still. Yep. Zoo is still here.
Okay. This is what you're going to do for next week. That'll be in the PowerPoint. I'll send that out by email. But I figured I'd put that in here to as incentive for the Sea Cadets. Persian Gulf 2002. And I think I'm down at the bottom of the questions here. Okay, Chris, good on that. Yep. I did my combat control officer course at HMCS Skeena. There you go. Okay, any questions from anyone else? Yep. Okay, Mike, here. It'll be in the email I send out. Review chapter 2, read chapter 3, and go through RIC 3, and that's the link. I'll send out by email tomorrow. Okay, any other questions? Whoops. Okay, take care, everyone. Have a good night. I guess it's good afternoon out in BC.
Good night to you too.
Yanni, you're a bit distorted. What'd you say?
I said, have a good night, you too.
Okay, take care. I'll stop recording.